Welcome to the penultimate lecture in this course. We're going to look today at control strategies and PID. So control strategies. There are three forms of control strategy. Basically they are open loop, feed forward, and closed loop. So we're going to look at each of those and see what each one looks like. We've covered them or we touched on them all before, so this part, nothing really new. This is an open loop control strategy, and some issues or considerations around the open loop control strategy. If you have an open loop controller, if you want your output to reflect your input, then that means that you have to have a very predictable plant, right? And you also have to have a controller and control action that is how I describe well informed. So it means that whatever your input is, if you want to guarantee or have a good level of confidence the output is going to reflect your input or your demand point, then you have to be able to map effectively or have a controller schedule which is very well informed about the plant behavior. So you know when that control action gets applied, then the plant is going to basically do what you expect it to do. And so the schedule must be accurate based on past performance. So you have to have a thorough understanding of how this system actually responds, how it works, what the system dynamics are. Of course, with an open loop controller, no disturbances are taken into account. So if you have disturbances in here somewhere, those things aren't going to be corrected because there's no feedback loop and there's no check on the outcome. So you don't know whether you're going to, or the system, let's say, does not know and can't adjust this control action based on the output. It's just a simple open loop. A next step would be something like a feed forward control. Feed forward control could actually have two different configurations. This is one of them, and this is where if disturbances are acting on the plant as is shown here. So for instance, if you've got a cruise control system on a car with the set point speed, and well, that might not be the best example, so try to think of a better example. If you have a, well, let's use an autopilot on an aircraft then, and you have sensors on the aircraft like airspeed sensors. If you're getting gusty conditions or like a headwind, then you could actually detect what that disturbance is which is acting on the plant and correct for it in advance by measuring it and adjusting your control action based on your measured disturbance. Right? So, or if you've got a lot of you used an example in the in-course test of like an air conditioning system. Say you have an air conditioning system cooling a room. If you were to have, for instance, an input that identifies when a door opens, that could be a disturbance. So you could automatically add more cold air, or you could adjust the control actions to say increase the fan speed of the air conditioning unit when a door opens, because when a door opens, then you're going to lose some cold air potentially, and the temperature of the room is going to go up. So you can preemptively correct that and reduce the amount of variability in the room temperature by preemptively adding more cold air. And there are a lot of benefits to feed forward types of control systems. The main one is that they can react faster. So rather than waiting for an output from a system to perturb or to vary from its set point, what you're doing is you're preemptively correcting for things that are going to affect the output state. Right? So that allows the system to respond more quickly than it would if it was waiting for the plant to change its state for the output to change before it then corrects it. So in a pure feed-forward condition control system, now this is one configuration where you're measuring disturbances and correcting for them preemptively, but you could also be measuring your inputs or your reference input, your set point. And if there are changes in your input, you could also preemptively act on those before you're detecting that error differential between the input and the feedback. Or you could have a preemptive change, adjustment of some control parameter based on your reference before your output starts to vary from the set point condition. So you could have feed forward on your input, your reference, or you could have feed forward from your disturbances. But in order to do this, you have to be able to measure and accurately incorporate your outside influences on your system. And that is only going to be possible, if you are able to effectively measure those disturbances. And it's particularly important if you have a system like this, which is basically open loop with feed forward control. And you're not measuring your output, you're not giving feedback in this system at all. Now, we're going to look next at the closed loop control system, which we're most familiar with. But what you can have is you could have a feed forward control system with what's called feedback trim. So you could actually combine both. And of course, if I had my little sketch pad, I would now draw on a feedback loop here. So you can have a combination of both feed forward and feedback. So the feed forward would take care of most of the variations if you're correcting, for instance, for a disturbance acting on the system. But there might still be some variability where the disturbance isn't fully corrected for based on the feed forward control. So you get an error between your output and your reference, then you can just correct for that in the normal way. So that's called feed forward with feedback trim. Of course, feedback control is the one we're most familiar with, where we have feedback on the output condition of our plant, and we're comparing the input and the measured feedback to determine a deviation or an error, and the controller multiplies the error by some algorithm to create a control action, and that control action changes the actuating conditions in the plant. Right, so again, where we started in the course was talking about automotive, about a car cruise control system. Right, so for that kind of thing, you've got your vehicle speed as the output, the vehicle is the plant, you're measuring the output speed, feeding it back and comparing it with your set point speed, which is set by the driver, usually with a button on the steering wheel. But you're comparing, but then it's stored as a parameter in the engine control unit. So the comparison would be done, the comparator is actually in the engine control unit itself. It creates an error. That error is then multiplied by a control action or controller algorithm that creates an output action, which is usually sort of a voltage that acts on the servo maybe of the throttle in the engine, if it's a gasoline engine, and then that throttle might be opened or closed based on the perturbation, the error, the nature of the error, whether it's overspeed or underspeed. Then, of course, that changes the torque output of the engine and the amount of torque at the wheels, the force, the tractive effort force, and therefore the acceleration rate, so you can accelerate back up to your desired set point to reduce the error to zero. So a feedback control system is always aiming to reduce this deviation or the error to zero. And the feedback control involves having to have a feedback loop, which means you need to sense and measure the output condition. That adds components to your control system, that adds cost to your control system and complexity, and you also then have to probably program a more complex controller. Right? This requires a comparison, like I said, between the outcome and the reference. And feedback control corrects the effects of disturbances by first measuring their effect and then correcting it. So, as I said before, it's slower in as much as when a disturbance acts on the system, say the vehicle goes up a hill, and that would be an unmeasurable disturbance, so you could only measure it based on the change in your speed, which is your output. So first of all, the system condition changes, then you're trying to correct it, which is inherently slower than being able to preemptively adjust the nature of the control action because you have detected and something happening to the system that needs to be corrected. Okay, so let's look at this system. It's a double pole system. So 1 over s plus 1 all squared is the system we're dealing with here. And so we have 2 poles at -1. We've got a reference coming in, disturbance acting on that reference, going through the plant to give the output, and we're comparing the open loop system with the system where we're getting feedback control, right? And again, K. So we're applying here, in this case, well, we're actually applying a disturbance. So this is the system that we're dealing with here, and we're going to vary the value of our gain. So we're going to compare our open loop response with our closed loop response with varying values of gain K. So this is what's going to happen. This is, you might see here, the input, or the disturbance rather, it goes from 0 to 10 at about 4 seconds, comes back down to 0 to about 12 seconds. So you have just a step up and a step down in the disturbance on this particular system, and it has a typical sort of response. It's kind of, I suppose you describe this as typical open loop response, as you might expect. So that would be with a gain effectively of 1. Let's say, no, I beg your pardon, it'd be the no closed loop is just simply open loop. So no feedback system. When you just apply a feedback system, you close the loop and you still keep your gain at 1, you can see that the response is already much better managed. So now by applying a closed loop response, instead of the system going all the way up here to 10 in response to the disturbance, now the disturbance is better suppressed, but it's not ideal because you're still getting a perturbation from your set point of 0, about 5, right? So still not great, but getting a bit better. If we continue to increase the gain K, then you can see that the amount of perturbation for the same disturbance of 10 acting at the same time is now much less. So we're kind of getting the system disturbance managed here, but we've still got some going on. So ideally, you'd want to try to get this system disturbance response to closer to 0 as possible. So when a disturbance acts on the system, it reacts very quickly and corrects for that disturbance. But you can see the benefit of applying that closed loop control, and especially as you increase the gain in that closed loop controller, it helps to resist disturbances acting on it. So we've looked so far, I think almost all our examples would be like this one, which is where we've got a gain of K, which is a proportional gain, just a multiplier. So whatever your error is, you're multiplying it by a scalar factor to give an output, which is X, K times your error. We can see that as you increase your gain, you're multiplying up the effect of that output and suppressing the disturbance. What we're going to look at now, though, is 3-term or PID control. So PID control is a very, very common form of control system, and we're going to look at just how common it is. We'll mention that in just a minute, but for any control system, before we get into looking at PID, for any control system, we usually require 3 properties of performance specification to be satisfied. So generally, we want good stability, which is a lot, it's all those parameters around things like the response of a system to a step input. So we want our system to be reasonably responsive, to have a fairly quick rise time, fairly quick settling time, overshoot from in response to a step input that's not too excessive. So we want good stability. If it's a disturbance we're dealing with, if a disturbance acts like in the previous example here, we don't want the overshoot to be too high, we want it to settle quickly. Same criteria really. We also want zero or at least small steady state errors in responses to change in input. So, or in response to disturbances. So we want a system that can eliminate steady state errors, and when the transient part of the response to a change of disturbance or a change of input is settled down, we want the output to match the input. And then, of course, what we're looking at just now, the rejection of external disturbances. So these are the three fundamental criteria we'd be looking to have delivered by any control system that we design. PID controllers are a standard solution to control problems. About 90% of industrial controllers are PIDs. So that goes to show how prevalent they are. Very, very common form of controller, especially in industry. And all the time, the PID, the objective of a control system is these three things: good stability, reduce the steady state error, and be able to reject external disturbances. In reality, a lot of industrial controllers are focused on number three, actually, especially in process plants, which are prevalent in our industry here in Trinidad and Tobago. So because we have a lot of process type plants, those tend to run in steady state. You want that plant just to run at a constant rate without any effects. So as temperature, that atmospheric temperature changes, then if this process is sensitive to temperature changes, for instance, then you want the process, any control system you have, to reject the impact of that disturbance. If you have, say, a change in the density of your product for some reason, then you want the system to be able to react and to reject that disturbance of the change in density and maintain a constant flow rate. So it's that kind of thing which is particularly important for process industries. So your PID controller in many cases will be seeking to reject external disturbances and maintain a steady state output. For the three-term or PID controller, we have three elements, obviously a proportional, an integral, and a derivative. So let's look at each of these. The proportional term is the one we're most familiar with. It's the most basic controller. It takes the error and multiplies it by a gain. So that gain is a scalar. You just get an output or control action or a control signal, which is the error signal times this scalar multiplier called gain. So just put in simple mathematical terms, our control signal, we're calling that M, our error signal E, and M equals Kp times E. And this will mainly affect the speed of response, but it will also, if you increase your gain, and depending on the exact transfer function of your system, it could also actually degrade relative stability. So there are some sort of checks and balances on this. You can get a faster response, but it might be more oscillatory or less relatively stable. So high gain will destabilize the system whilst reducing the steady state error. So if I go back again to this slide, you can see here, as we get the closed loop system and then increase gain, we've reduced the error that's affected by that disturbance. So that's what the higher gain is doing, but we're also increasing relative instability. So you can see the amount of overshoot here. When you have no open loop, you have no overshoot. This one has a very slight overshoot. As you're increasing the gain, you get a slightly higher overshoot before a slightly longer settling time. So that's something to be borne in mind. So high gain will destabilize the system whilst reducing that steady state error. Let's look at the next element. Next element is integral element. So the integral action in our PID, that follows, no surprises here, an integral rule, right? So our control action MT equals some factor Ki times the integral of our error over time. So we're actually adding up our error. So if our error remains constant, then, and it's not coming down, then our integral actions, our MT that comes from the integral part of our controller, our PID controller, if Ki is a constant or a weighting factor, it's fixed, then as time goes on, if the error is fixed, then you're just going to be ramping up in a steady way the control action resulting from the integral. So it basically tries to drive error out of the system, especially error that will be continuous error or a steady state error. Right? So it increases the accuracy of the system by reducing that steady state error. Any steady state error, if you have an error that only lasts a moment, you're not going to get much control action from this, the integral part of the controller. But if you have an error that hangs around a bit, in other words, some kind of steady state error, then you're going to get the integral action is going to become very significant. The problem with integral action is it does degrade the stability of the system. And because it basically introduces that an additional integral term in the denominator of the transfer function. So the third part of our three-term controller, our third term, is our D term, standing for derivative. And just as integral adds up the error over time, the derivative action looks at dE by dt, the derivative of the error. So what we're looking at here is the derivative or the rate of change of the error times the weighting factor Kd. Right? So we're looking at the rate of change of the error. So in other words, if you're having an error that's changing quickly, then you're going to get a lot of derivative action. Your MT, if you have a high rate of change, doesn't matter if the error is large or small, it's looking at the rate of change of the error. How fast is this error changing? Multiplies it by a factor Kd, a derivative weighting factor or a derivative gain to give us our control action from the derivative part. So this one has no effect on accuracy. It doesn't matter if we have a steady state error and it's not changing, it's just a fixed error, a constant error, then this is going to be zero because the error is not changing. So it doesn't have an effect on the accuracy or the steady state condition of our system, but it does stabilize the system when it's changing fast. It slows down or it seeks to compensate for an error that's in flux, it's changing. The problem with the derivative action is it can actually amplify noise. So it allows, if you have a noisy error signal due to signal either a system which is mechanically vibrating or some noise on your electrical system, then it could be that this actually amplifies that and makes it much worse, because the noise would typically have a very high rate of change, and then when it has a high rate of change, that would be detected by this derivative action and amplified. So that's a concern and something you have to be conscious of with derivative action. So we can put all three together. Our overall action MT is going to be our proportional action times the error, that's the simple one, plus our integral action times the integral of our error over time, plus the derivative action times the rate of change of our error. So you have three terms, 1, 2, 3, our P, our R, I, and our D, and each of them is dealing with a different sort of condition in our error signal. And the key really with the PID controller, and this is what you've been doing in the lab, I think just a few of you now, just one or two groups remaining to go through the second lab. And in the lab, you've been tuning a PID controller. So the key is, how do you set your KP, KI, and KD terms to get the kind of response that you want? And that's really where, this issue of PID control or calibration, control strategy design, all those sort of things start to come in. So to tune your PID controller, you do want to take a systematic approach. And there are certain standard ways in which it can be done. None of them is perfect, but at least it allows you to get a good estimate, initial estimate for your terms, your KP, KI, and KD. All right, so how do we tune our controller and get those KP, KI, and KD terms? Oh, by the way, this is the block diagram for our controller. And this is useful because it's PID, P at the top, I in the middle, D at the bottom. And you can see that it's the addition of those three terms together that gives you your overall control action. So you can set any one of these to 0. You could set the KI to 0 and just have a PD controller. We have proportional and derivative action only. You could cross off your derivative action, have only a proportional controller. You could cross off your proportional and derivative, just have an integral controller, so that you can mix and match the type of controller you want based on your requirements. So let's have a little look at an example here. It's the same example. Oh, beg your pardon. Thought it was, it's not. Okay, so we're going to look at a type 0 system under proportional control. It's just second order type 0 with two real roots here. Very straightforward type of system. This system has a finite steady state error in response to a step input, and it can't follow a ramp input because that's what a type 0 system is like. We know from our previous lectures that when you have a type 0 system, then it can follow a step input, but it's going to have a steady state error. It can't follow a ramp input, right? So if we just have a proportional gain, then that's going to be the condition. What if we convert the proportional controller K into a proportional plus integral controller, or PI? So if I just go back to my previous slide, then what we're saying here is we're going to keep our proportional control, and we're going to introduce an integral control, but our KD is going to be 0. Right, so we're converting our controller to a PI type. So now, instead of just a K, proportional, we're going to add our integral action. So this is what our new transfer function for our controller will look like. It's going to be KP plus KI upon S. Again, directly from this block diagram here. So because any two blocks in parallel, you add them together. So just dropping off our KD. So our closed loop system will now look like this. We've got our input, we've got our PI controller, our basic plant, and now our open loop transfer function. Our open loop transfer function is going to look like this. Basically, if we multiply out our KP over plus KI upon S, you multiply KP by S, and you get KP S plus KI upon S. All right, so you can then divide that top line by KP, so you get S plus KI upon KP. So that's what you have here, with the KP taken outside. All right, S plus KI upon KP. The KP is outside. So this is our open loop transfer function now. And you see, importantly, you have this S here. So it now becomes, instead of a type 0 system, it becomes a type 1 system. And what are some of the characteristics of a type 1 system? Well, firstly, the type 1 system has no steady state error. in response to a step input, and it can follow a ramp input with some finite steady state error. So it's now become a more capable system because it's now a type 1. Right, so that just gives us a sense of our PID and how we might introduce in our integral and derivative elements into our controller to get the kind of behavior we want, right? Now, most controllers in industry are digital controllers. So we're dealing with analog control through this course, but I just want to touch on terminology that relates to the digital form of PID control, because that will be more common in industrial context. So a PID controller, when it's in a digital system, is described or written, or the terminology that's used is weightings, right? So, and the analog controller is generally described in terms of a proportional band, an integral action time, and a derivative action time. So you could either have your weightings, which are Kp, Ki, and Kd, or you could express the PID control parameters, like how much proportional, how much integral, and how much derivative action do we have in terms of these action times, Ti, Td, and our proportional band, P. So these are also very common in industry. So a digital controller generally would have Kp, Ki, Kd, but your analog control, which is still a fair bit of analog control historically in industry, they would use these bands, your P, your integral action time Td, and your derivative action time, integral action time Ti, derivative action time Td. So let's look at how these are calculated or determined, because controller settings are often given. I wouldn't say usually, but in many cases, oftentimes they are given in terms of PB, Ti, and Td. In fact, even for digital controllers, they're often set up, because it's sort of a legacy thing, they're often set up to still have the gains for each part of your PID controller expressed using these PB, Ti, Td terms, right? So you need to understand where they come from and how you get them. Right, so we're going to consider a proportional controller here. Very straightforward. We're pretty used to this. Error signal in, control action out. If we have a system, a real life system, MT, your control action is not finite. Right, you're pushing a voltage out of your proportional controller, and that voltage will have a range. It might go from -5 to +5 volts, might go from 0 to 10 volts, whatever. So if we assume that our control action saturates at 10 volts, so let's say this one goes from -10 to +10, that's the highest control action you can get out of your proportional controller. So you might like to think you could get almost like an infinite output to give a very aggressive response to your error signal, but in reality your electrical and electronic system is going to be constrained to only be able to give an output of a certain finite value. So if we have a proportional gain, for instance, Kp of 5, then our error, if it just reaches 2 volts, then it's going to saturate our output, because 2 times 5 is 10. So the maximum voltage we could have as our error is 2 volts, and above that our output is going to saturate. So this will be the sort of relationship between our error on the x-axis and our control action on the y-axis. If we have an error of 1, fair enough, we have a control action of 5. 1.5, okay, 7.5, because we're multiplying by our 5. But if we get up to 2, then we're going to have this sort of condition where you can't get any more output. on your control action. It's literally saturated. So our proportional band, which is what we're describing here, proportional band P, our proportional band is basically the ratio between the maximum output of the controller and the input of the error, right? So if the error also has a range of 0 to 10 volts, you know, or let's say -10 to +10 volts, the control action has a range of -10 to +10 volts, then once our error gets to just 20% or 2 volts, 20% of its maximum value, then the control action saturates. Because if it's 5 here, you multiply 2 by 5, then you get your 10. So really, the amount of control action you can get from your proportional controller is determined by, you know, the output, or the relationship between the output, the control action, and the input error signal. So in that case, you know, in the situation we're looking at here, if our range on our output is -10 to +10 volts, and our range of our error is -10 to +10 volts, then our error reaches maximum control action saturation, maximum control action at 20% of its value. So we say the controller has a proportional band of 20%. And how does proportional band relate to KP? Like in this case, our KP is 5. So our KP equals 100% over our proportional band. Or you could, of course, switch these around. Our proportional band equals 100% over KP, depending on which way you're calculating, whether you're calculating your PB or your proportional gain. Okay. Now then, how do we assess integral action time? So let's look at a PI controller now. Our control action here is going to be the product, I beg your pardon, not the product, the sum of your proportional gain and your integral gain. So again, you might well get into a saturation condition, but the way we define our integral action time isn't to do with saturation in this case. If we consider the input to the controller, which is our error signal, and assuming that's a step input, then our error step input, our proportional action, or the M that results from our proportional part of this controller, is just going to be the green line, right? If you have a step input in your error, let's assume the system's not responding, so you have this delta between this error between your input and your current state of your system, then that's the output from your proportional part of your controller is going to be the green line, Kp times Et. But the Ki integral Et dt part, that is going to start to add up over time. So the red line is the ramping up of our integral action over time. If you have a steady error, then the integral action is just going to gradually grow and grow and grow because it's adding up the error over time, right? Now there will come a point in time, which we call Ti, where the integral action from our controller exceeds the proportional action. It's going to start low because there's not much time has passed. It's now just starting to add up. But there will come a time when the integral action actually gets to be the dominant part of the control action, or the control action output. Now, of course, this is going to be saturated at some value, so it won't continue to go for infinity or level off at some point because your output MT is going to have a saturation value. But the important parameter here is how long does it take? What's the integral action? The integral action time is how long does it take for your integral action of your controller to exceed the value of your proportional action of your controller. So at time ti, the proportional and integral components make equal contributions to the control action. Right? And if you have a higher ki, if you increase the integral action, then that leads to a decrease in your ti. You can see that this line is going to get steeper. If you increase ki, it's going to give you a steeper line because you've got a higher multiplier in your integral action. And the time it takes for that integral action to exceed the value of your proportional action is going to reduce. So there's a direct correlation or relationship between this integral action time ti and the gain or the relative gains, let's say, of your proportional and integral elements of your controller. So now looking at a PD controller. So this one has a proportional part and it has a derivative part. So of course now your proportional part is your normal scalar, but your derivative part is looking at the rate of change of your error as shown here. So again, consider the input to the controller, the error signal, in this case not to be a step, because if it was a step like it was here, then the gradient of this dE by dt would be 0, so you'd have no derivative action. But if we consider the input to be a ramp, so now the input, the error is gradually growing at a constant rate, it's a ramp error. So this is our error gradually growing, the blue line. Then what's going to happen, our proportional controller is going to have action, M, which also grows in proportion to the error. But the derivative action is going to be constant because this is a ramp, it's a steady gradient. So dE by dt is going to be constant times whatever your scaling factor kd is. So the green line shows you for this ramping up error what the derivative action is going to be. And you see, again, you get a time, td, where, in this case, your proportional action starts to exceed your derivative action. That is your derivative action time. So at time td, the proportional and derivative components in your output, your control action m, are equal. Right, so that's a key point, and that td is directly related to the relationship between kp and kd. And in many cases, to define how much derivative action you want in your system, you will be asked, in calibrating a PID, to set this value td. And if you set a higher td, then basically what you're doing is you're increasing your derivative action relative to your proportional action. So for ti, your integral action time, if you have a smaller ti, you have more integral action. But for your derivative control, if you have a larger td, you have more derivative action. Ronell is asking for me to explain why kp is increasing. Kp is increasing because we are applying a ramp. We're assuming that our error is ramping up. Right? So if our error is ramping up, this is our error here, is gradually growing at a constant rate. Now, you have to do that because, to determine your derivative action time, because if you had a sort of a constant error as a flat line, that would have zero gradient, so you'd have zero control action from your derivative action, your derivative part of your controller. So for this one, we define that the error is growing at a steady rate. So we're defining that so we can define what our derivative action time is. So when we define that the error is growing to a steady rate, then our action, our control action from our proportional controller is going to be the error times Kp, and the error is growing steadily, so our Kp times our error is also going to grow steadily. It's a ramp. But because the error ramp is constant, we're going to get a constant rate of change of error, dt by dE, multiply that by a derivative action kd, gives you this green line. So if we change kd, we'd be really moving the green line up and down. And if we move it up, we're increasing our derivative action, then we're going to move our time, the key time when the proportional and derivative actions components are equal. We're going to move that time to the right or increase the time. If you increase your derivative action, your kd, this is pushing the green line upwards, it's pushing td outwards, and you're increasing your integral action time. So if you are increasing your integral action time, then you're increasing the proportion of derivative control in your system. And I just contrasted that to the integral action. With the integral action, we're assuming a steady error, and that steady error means that the proportional part of our control actions is steady state, is just going to be a fixed value. But because you've got an integral here, you're adding up the area under the curve, under the green line. And of course, that area is gradually growing to the point where your integral action, the red line, equals the amount of m, from your proportional controller. That's Ti. Now, if we increase our Ki, then this red line will get steeper. So if we have more integral action in our controller, then our Ti, our integral action time, is actually going to get smaller. So these two, the integral action time and the derivative action time, they actually move in opposite directions when we increase the amount of each one. If we increase the amount of integral action, our integral action time gets smaller. If we increase the amount of derivative action, our derivative action time gets larger. And if we're calibrating a controller, especially in an industry context, you might have, for instance, a PLC controller with where you can set the parameters for a PID controller inside that, and it might well ask you for your proportional action or proportional band, integral action time, and derivative action time. And really, with the integral action time and derivative action time, what you're doing is setting the amount of derivative action relative to the amount of proportional gain. And so you can see that clearly here, well, probably even more clearly with the integral one. If you change your proportional gain up and down, then the green line shifts. You're going to change your integral action time. So, for instance, if you keep your integral action Ki fixed and you reduce your Kp, then this green line is going to come down, and your integral action time is going down. So, relatively speaking, you're actually, increasing the amount of integral action compared to the amount of proportional action. With the derivative action, if you are increasing Kp, let's say you're reducing Kp, then the gradient of your blue line is going to come down, and your Td is going to increase. So you can reduce your proportional gain on your system, and the impact of that is that your derivative action time is going to increase. So again, Td and Ti, they're not just a function of your Ki and Kd, they're a function of the relationship or the proportion of derivative action compared to proportional action, the amount of integral action compared with proportional action. All right, one important last section, talking about how to tune, like some standard approaches to tuning a three-term controller. And when I say tuning it, I mean setting these three terms, our P, I, and D. And this is like an historical method that was derived by these guys, Ziegler and Nichols. There are two methods we're going to look at, and they're both derived by Ziegler and Nichols, who were kind of some early guys in developing control theory. They use these experimental methods. But when they did their work, when they did their research and came up with their methods, they were using control systems again for process control. And that's the kind of like the point leases or process industry type situations. And process industries would have very slow, long time constants. And time constants really as high as up to about 30 minutes. So this is not a kind of robot arm control or the kind of control you might have for the DC motor that we're doing in the lab, just very fast or relatively high time constants. It's not the kind of control you might have in an autonomous vehicle, which is at the other end of the spectrum, super high, super fast. But so bear in mind what type of system they used when they came up with this method, and there are certain implications to that if you use it for a different type of system, which you can still use it, but you have to just adjust it accordingly, right? So the ZN or Ziegler-Nichols settings, again, because it's process control, primarily designed for disturbance rejection, and they tuned the performance to a quarter decay ratio, which means that every oscillation after a response to a disturbance or a change in your input, it's expected that the decay would be a quarter of the previous sort of spike, which corresponds to a sort of damping ratio of about 0.3. So if you have this decay ratio, it goes down to a quarter of its previous oscillation magnitude each cycle, then that's like a damping ratio of 0.3. And like I said, many applications require minor to major adjustment to these settings so that you get a higher damping ratio. But what it does do is it helps you to get a reasonable starting point for the relative values of your P, I, and D. So you kind of get them in the right ballpark, and then you can just fettle them. That's a nice word, isn't it? Fettle. You can fettle them from there, and that means make fine adjustments or fine tuning. For some plants, the continuous cycling test is too hazardous. We're going to come to look at what that is in just a minute. There are two types of tests that you can use. One is continuous cycling, and the other is reaction curve. And depending on the type of plants, the continuous cycling test can be too hazardous, so you might use a reaction curve. So what is the continuous cycling method? In this method, you basically put your plant under closed-loop proportional control, and then you adjust the gain until the system is marginally stable, which means it goes into simple harmonic motion. The system oscillates continuously with constant amplitude. So you can understand why, for some systems, this is kind of dangerous. And you can't really do it for every system, but some systems you can. If, like, again, the lab that we did, the DC motor controller, that you could afford for that to go even unstable, and it won't cause any damage. So it's a safe system. You can put it into a marginally stable condition to get your initial PID values. But many systems, that you can't do that. Say you've got an elevator and you're trying to set the PID values for the elevator. You don't want to set your elevator into a marginally stable condition, because if your elevator became unstable, it could end up in a big disaster, right? So just think about whether the system is compatible with a continuously cycling method. Even an industrial plant might not be, because if the system becomes unstable, you could end up with an explosion or something in the worst case. So, but if you are able to use the continuous cycling method, then what you do is you tune or you adjust your proportional gain only. You haven't got any I or D control on at this point in time. You set those to 0, and you're just using your value of your proportional gain. You're adjusting your proportional gain K until it becomes the system becomes marginally stable, and then you're measuring. Right, you're noting the value of proportional gain K0 that gives you that continuous cycling condition, and you're measuring the time period between oscillations, T0. right? And those two values, K0 and T0, they become the basis for your PID settings. And these are the settings. So your gain should be initially set according to Ziegler-Nichols to 0.6 times K0. So if you have a marginally stable condition with, say, K of 5, then you would set your K0 to be, well, 3, right? Your integral action weighting factor, Ki, is going to be 2 times your Kp over T0. So you take your Kp first, multiply it by 2. So if we said we had 3 for our Kp, then 2 3s are 6. And so we had 2 seconds, so we have 4 seconds for our cycle time T0. So with 6 over 4, sort of 1.5, right? So our Ki got a value for it, assuming a couple of simple assumptions. K0 is 5, T0, what did I just say? 6, was it? I can't remember what I said. Anyway, 3, something like that. All right, so then derivative action, Kd. I don't know why this is a capital D. It should be K subscript D. Is going to be your Kp times T0 over 8. So again, let's just assume K0 is 5, T0 is 4. Right, so our Kp is going to be 3 times 4 is 12, 12 over 8. 12 over 8 is, again, that's 1.5, right? So you have, based on that, Kp is 3, Ki 1.5, Kd is 1.5. So we got our values. Like I said, if you use your continuous cycling method, the settings you get that we just got for my assumed numbers, they'll give this sort of quarter decay ratio. So that means the amplitude of our first oscillation A, well, the amplitude of our second oscillation B is going to be 1/4 of the amplitude of our first oscillation A. And that gives about 3 or 4 oscillations before settling, and a zeta damping ratio of about 0.3. And the system then functions kind of as a regulator. The regulator removes disturbances and has to be quite aggressive in doing it. It has to aggressively eliminate any disturbances in the system. So that fast response, that low damping ratio, corresponds to an aggressive management or mitigation of disturbances in the system. Let's look now at the other Ziegler-Nichols approach, reaction curve method. This time, instead of putting the system in a closed loop configuration, we're using it in an open loop configuration. And this one, we're applying a step input, measuring the output. And the controller settings are based on parameters of the reaction curve, the output response to this set input, step input. So this is our input here of a certain value, and the red line shows us the output response. And this again, open loop, no feedback. So in this case, we're looking at 2 parameters. These are a little more difficult to derive, more difficult to measure accurately, so you have to use some judgment here. And you're looking at the average slope of your reaction curve, which is called N. And we're also looking at the lag time. So if we first of all sketch or draw, find this slope, and then where the slope intersects with 0 on the y-axis, you measure the lag time between the 0 time and where that slope intersects with 0 on the output, right? Where it intersects on the time axis. Once you've got those values, your Kp is U over NL. Right? So say we put an input of 2, we've got a slope of 3, and we've got a lag of 1. right? So we'd have 2 upon 3 or 0.6 for our Kp. And then our Ki is Kp upon 2L. So that would be 0.6 divided by 2, or 0.3 for our Ki. And our Kd would be Kpl upon 2. So that would be 0.6 times 1 is 0.6 upon 2. So again, our Kd would be 0.3. So interesting, because you see that they're generally, I just kind of pick numbers a little bit randomly, but the way the numbers work is that we've got a similar Ki and Kd for both reaction curve and continuously cycling method. Well, not similar numerically, but relatively, right? Ki more or less equal Kd, and Kp was basically twice Ki and Kd. So you sort of see how the relative value or relative magnitude of your three terms came out somewhat similar from the two methods. All right, so just to wrap up with a bit of an example here. So I'm not going to go through it in detail, but we're looking basically at, again, the same system, but now instead of just having a proportional gain like we had here to control our system, this is our open loop response. Then we applied closed loop feedback with a proportional gain only of 1, and then a proportional gain only of 5, right? So we already had those data from before. Just didn't go to the right place there. Right, so now, well, this is our proportional gain with different values. We saw our open loop came up like this. This is 0.5, 2, and 10. We saw 1 in there somewhere before and 5 in there somewhere before. So that's what we're getting with just proportional gain. So if we have 0 for Ki and 0 for Kd, and our same disturbance, a disturbance being an input of 10 at time 4, dropping back down to 0 at time 12. So sorry about the sketches. I was trying to generate this on MATLAB, but didn't quite have time to do it. These are some nice old hand sketches. Okay, so we're seeing here the same system basically, but now we have PI control, and we're using K equals 2. So we're using this red line here as a baseline, but as you can see, our step input, our disturbance occurs at 0 time. Right, so this is our baseline K2 with PI, with our integral action time being infinite. In other words, we don't have any integral action. This is our baseline here. Right, then as we start to introduce infinite integral action time, means that the integral action doesn't exist, right? Because remember, a smaller integral action time means more integral action. So if we now go to an integral action time of 5 seconds, then you can see you get more overshoot, but the system settles down and completely rejects the disturbance after about 10 seconds. And then when the disturbance is removed, you get a sort of fairly aggressive correction taking place with the Ti equals 5, and that's this one here. With the Ti equals 1, so you've now got more integral action because we've got a shorter integral action time. So just to remind you all of that one, you have more integral action if your Ki goes up, the Ti goes down because this line gets steeper. Right? So we're keeping a constant Kp, but we're making the red line steeper by increasing Ki or by reducing Ti. So the first value of Ti was 5, now we've reduced it right down to 1, so it made this line a lot steeper. So when Ti equals 1, it actually rejects the disturbance a lot more quickly, but again, you see it has more settling time, or longer settling time, more oscillation, slightly worsened relative stability. So let's go to the next graphic. This one, we're using a baseline of k equals 1 and ti equals 1 second. So we're using this 1 second, but we've actually reduced our ki down, our kp down to 1 from 2. So, but now we're implementing derivative control. This is our baseline at the top with no derivative control. TD equals 0. Remember, if you have a low TD, then you have less derivative action. As your derivative action increases, you're going to get a higher level of TD. Right? So as derivative action increases, your TD is going to get bigger. So we're going from 0, which means there's no derivative action down here, and then basically pushing this green line up to increase the amount of derivative action, increasing KD. So increasing it from 0 to 2 seconds, and you can see what's happened here is that the amount of overshoot you get in response to the step into the disturbance is much lower. So it's gone from, you know, up to about almost 4 on the output, just to about 2. But you slightly extend the response time. So it's a trade-off. Now you're into tuning. Now you're into fettling and changing these values till you get a setup which meets your performance requirements, which you should have set at the advanced start of your design process. Right, so this is to summarize. In tuning your 3-term controller, you basically have a number of steps. You first of all can set your proportional action to give satisfactory response time, overshoot and steady state error. You can use the Ziegler-Nichols and get starting points for your integral action and derivative action. You can introduce your integral action with sufficient weighting to reduce the steady state errors to an acceptable level. So that's what we did. That's what we did here. Right, we gradually introduced from 0 integral action with what we reckoned was a decent proportional response. You know, we introduced a bit of integral action here. We saw how it had an impact in reducing our steady state error that was caused by that disturbance. As we increased our integral action, improved the performance of the system. And then after that, we can then start to increment that derivative action to get an acceptable overall time response, which is what we did here. Right, so we edged up our derivative action until we got a response that we were more happy with. So that's a general process. It's kind of not rocket science, but it's calibration. It's going back through, adjusting, fettling your system till you get a response that you're happy with, at which point you can settle and seal that response as a settled design.